All right, good morning, everyone. Welcome to our second day of class, kind of our first real day where we cover stuff. Reminder, for those that weren't here on Monday, this is Physics 2, 2049. I'm Dr. Wesley James. Again, just making sure everyone's in the right spot. Just a quick reminder is one, there's no recitations or discussions this week. I don't know if I mentioned that. There's no recitations or discussions this week. I'll send an announcement about that to make sure everyone's aware. Those will start this coming week. So those will start I already sent my first announcement I sent out had that detail. So those will start next week on the 19th. Speaking 19th, remember Martin Luther King Day, there's no classes, campus is closed. That is true of this class and all your other classes. And last thing, remember there is every single class, you all have an assignment the first week of class. It's for financial aid to make sure that you actually are enrolled in the class and all that stuff. So make sure you all do this. It's a really quick and easy thing. It counts towards one of the quiz grades. So it's an easy way to kind of get that grade started well. It's just some quick questions about the class and things like that. Easy peasy. No physics actually in it. Make sure you get it done. We're going to actually start doing stuff today, talking about the things. Hopefully we'll actually get through this whole PowerPoint today and tomorrow. We won't get through it all today. We'll finish it hopefully on site tomorrow, Friday. Couple of reminders. Remember to sign up for iClickers. So today, and I sent out with my first announcement, I sent out to you all, I have a couple key points. One was no discussion about the patients. The other was how to sign up for iClicker, and specifically that the grades are not going to count for iClicker until the 23rd. The 23rd is the first day it will actually start to count as a grade. However, I will start asking iClicker questions now, and the reason I do that is to make sure it's working for you, to make sure your thing is connected, to make sure that the points are actually being awarded to you appropriately. So I will be starting asking them, and they will end up getting posted on web courses, but the only purpose of that is so that you can see that the points are transferring, that everything is working as intended. When we get to next Friday, I will reset those points. I'll delete all those points from the iClicker thing. I'll delete all those polls, all that kind of stuff. So don't stress about it. I'll send an announcement on it because I get a ton of emails about it. If you do not enroll today, Friday, Wednesday, you will be fine grade-wise. I will ask questions just so you all can see how it works and then make sure it's all working and things like that. So keep that in mind. Awesome. So this whole PowerPoint slide is going to be on electric charge and forces. So something in physics that hopefully you saw in Physics 1, something unique to physics is that physics is a field where we look at the world and we try to understand how it works. That is all physics is. You look at the world and you try to understand the laws and the rules that govern it all. Now, the reason I say that, there's an important caveat to this that sometimes people get mixed up. Physics is not absolute truth. Physics is not absolute truth. It is our best understanding of reality at this time. We have been wrong, we will continue to be wrong. That is true of all sciences. Sciences are done by humans. Humans make mistakes. Now, it doesn't mean don't trust science. It's fairly good. The stuff I'm teaching you has been used for the past 200 to 300 years. However, there has been many cases where people have been proven wrong. Way back when, they thought the Earth was the center of the center of the universe. Oh, it wasn't. It's, the universe, who knows what the center of it is. The sun is at least the center of our solar system. Even the stuff you all learned in Physics 1, we learned at the beginning of the 1900s that was not accurate at a really small scale. So quantum mechanics came into play to understand things at a really, really small scale. This still happens. Then special relativity and general relativity also came into play because we thought we understood gravity. It turns out we didn't understand it all the way, and that will keep happening. So the reason I say this is everything I'm teaching you is our current best understanding. And even some of the things I teach you, I'll put little asterisks next to them, and I'll say this is true, kind of. It's good enough for you all. There's actually, we've discovered more things and it's more complicated than this. But for us, it's good enough. That'll actually be one of the first things I teach you about charges. What I'm going to tell you is good enough for you, but it's not actually the full truth. So, I mentioned that just this is how physics work. We observe reality, we come up with an explanation for it, and then we build from there. But everything is based on observations of reality, and then we go from there. And it's super interesting. I find that super fascinating. In URL's engineering, and everything's going to be built one on top of the other. We will not skip any steps. Now, engineering and things like that, you will get to later courses where they will just say, here's an equation. Don't worry where it came from. You will get a PhD to understand that. And that's fine. That engineering, you have to do that because you all can't get PhDs in every single equation, every single field. It's just not feasible. But at least in this physics course, we will, from foundations. In physics majors, your courses will continue to be that way. Engineering majors, you don't have the time to do that for the stuff that you get into. The real world is too complicated for you all to get PhDs and all the things. But whatever. All right, so just some background. Last time we did the syllabus, watch the video, look over the syllabus if you have any questions there. So things that you might need to remember from previous classes. You'll need to be able to do algebra, shock out. You're going to get plenty of practice with that. Trigonometry, you better be good at vectors. Vectors are going to be showing up for the rest of this class and for most of your future classes as well. Remember how to split them into components, recombine them. Now, in this specific example, I have how to get the x component. It has cosine. Do not get in the bad habit thinking that the x component is always cosine. Sometimes it is, sometimes it isn't. In fact, one of the problems at the end of the PowerPoint, it won't be. Just to remind you all that it's not always, but people get in the bad habit of that. Calculus, you all should be good at derivatives. You should be good at integrals. Derivatives will be no problem. The integrals, the thing that's going to be new in this class, is you all have had a lot of classes where you've learned how to do integrals. What you haven't had much practice on is how to build integrals for real problems. So all your math classes, they said, here's an integral, solve it. This class, we're going to build the integrals. And all the integrals we build, anytime I have y'all solve an integral in this class, it's going to be like Calc 1 level. We're not going to do any Calc 2 level integrals, no trig sub, no things like that. Because the complexity won't be solving the integral, the complexity will be building it. Actually making an equation that represents things, giving this idea that an integral is an infinite sum. So if I can find one small piece, then I can do an integral and get all the pieces. Yay, we'll see it when we see it. But that'll be a new skill that's going to pop up. You may or may not see it in Physics 1, but you'll get practice in here. Vectors, scalars, vectors, magnitude, direction, scalars just have magnitude. There's a reason we run energy. Energy is not a vector, so you don't have to deal with vectors. Units and variables, making sure you remember which one's which, X, Y, Z. We are going to see distance represented in so many different ways. You all have seen this up to this point, so you all can represent how far something has traveled with X, or Y, or Z, or R, or D. You're going to see that, or H for height. All of these are variables that represent distance, but different things. X, left, right, Y, up, down, Z, in and out, R is radio, well. That's going to show up in this class. That's a really common mix-up people have. Again, we're going to get practice on that, more and more of that. Free body diagrams, you're going to have forces in this problem. In fact, that's this PowerPoint. The first thing we observed regarding charges and the forces that they exerted. F equals MA, it's Newton's second law. Conservation energy is going to pop up in like 3 weeks for one type of problem. So, the things used from Physics 1 are still going to show up in this class. Okay, this process, the problem-solving strategy, this is the explicit process that every single one of you make every single day, hundreds of, I don't know how many times, a lot. When you woke up this morning, and if you were hungry and you decided to make breakfast, this is a decision tree that you went down. First you said, what am I going to solve for? I'm hungry. Second step, okay, you didn't draw a picture, we'll get to that, that's specific for physics and chemistry. You identified what you had. You went to the pantry, you went to the fridge, what food do I have? Then you figured out how you're going to combine those things to make the thing you actually want to make. Then you made it. And then at the end, before you ate it, you hopefully looked at it and said, yes, this looks edible. If it looks like trash, you're not going to eat it. You do this all the time. However, most people don't explicitly think that they're doing this, don't realize they're doing this. In STEM courses, it's very useful to remind yourself that this is the process you're going to use to solve problems. Because it's very easy when solving a problem to read a problem, be confused, and then just be stuck and be confused and not know what to do. What do you do in that case? This process. Remember, this is the process used for every problem solving. So if you're not sure what to do, go through this explicitly. You're going to see me do this when solving problems. You're literally going to see me in problems number step 1, step 2, step 3, step 4. Step 1, I'm going to identify what I'm solving for. I'm going to draw a picture. In that picture, I'm often going to put what I have as the givens. I'm then going to identify the equation. I'm going to be explicitly mentioning this because when you're stuck, this is what you lean on. This is the thing you're doing, whether you realize it or not. Whether you're writing down these steps, whether you're explicitly thinking through them, you are doing these steps. This is how you're solving every single problem in life. And this is what you're going to get really good at. This is what makes you a critical thinker. This is why you get paid for these jobs. This is something that I have noticed as I've gone more and more in life. People are intimidated by things they don't understand. People are intimidated to start tasks that they feel like they don't know what to do. And as engineers, as computer scientists, as physicists, not freezing is one of the most important things, and realizing that you're just going to go through this tree. What is wrong? So, examples in my life is like fixing my refrigerator. So the problem is like normally someone might hire someone, but you can do that yourself. It's not a hard task to do. First, what's wrong? It's not turning on, it's not doing that, it's making XYZ noise. Okay, so first step is wrong, then you identify what's going on in the system, then you look up things, and internet, ChatGPT, all that stuff. And then you try stuff, and you try stuff until it works. If you're lucky, it works. If you're unlucky, it breaks. Whatever. Worst things worse, if it breaks, it's already broken. This is, as a physics major, this was the most important thing I learned, was how to critically think. And this is the process I became really good at, and the process that you all will need to be really good at. Your job is not doing stuff that's already been done. I mean, if you are, you're not getting paid as much as the people that are doing stuff that hasn't been done. So you got to be a good thinker. All right. So you're going to see me do this a bunch. This is key. Units. Don't forget your units. Don't forget how to convert units. So here's a big table of unit conversions. I'm going to highlight the ones that we're actually going to use in this class. There's going to be some new ones that you might not have seen before, and you're going to see them a bunch when we see them. So mega will kind of show up, that really won't show up until we get to waves. Mega is 1,000,000, 10 to the 6. Kilo, you've seen that one, that shouldn't be anything new. Base unit, not surprising. Centa is going to show up, milli is going to show up, micro is going to show up, and nano is going to show up. We're going to be working with the smallest things, quote unquote, the smallest things, specifically electrons, protons. So we're going to be working on the nanoscale. Nano is 10 to the minus 9. And that is 1 order of magnitude larger than the size of atoms. Atoms are, so these protons and electrons are smaller than nano, but that gets us in that regime. So real quick, just something I also want to point out is you're going to notice me using this E notation in this class. So instead of using scientific notation of 3 times 10 to the minus 3, that takes a lot to write, and it also can look a little bit confusing. If I write this, if I write it too quickly, you can mistake that X, that multiplication sign, for an X. You can replace that 10 to the minus 3 as 10 minus 3, because I didn't write it in the superscript and things like that. So because of that, I opt to use the following notation. You use whatever you like. It's the same thing. These are 2 different ways to write the same thing. I'm not going to argue why I use this one, but use whatever you want. It really doesn't matter. I'm just telling you why I will use this. E to the minus 3, these are the same exact things. This E minus 3, 1 is shorter. 2, that E that's kind of slightly smaller, there's no other variable. We use E for electric field, but this E is kind of like, no one ever mixes this up. When you put this minus 3 after it, no one's subtracting 3 from E. That doesn't make any sense. So you're not going to get confused there. It's shorter, it's less likely to be confused, and this is also the way that you often plug it into a calculator. It's both the way you plug it into a calculator, and if you're doing any programming, scientific notation is often done by E, whether it's a lowercase e or a capital E, depends on the software language. So I like this notation because it's what a lot of other things use. Something I want to point out here then is one of the benefits of, so great, that's my scientific note. That's the way I do scientific notation. I'm going to really quickly write some common unit conversions. If you need to convert from kilometers to meters, all you do is chuck an E3 after whatever the number is. So if I want to convert 1 kilometer to meters, I put an E3 after it, times 10 to the 3. I don't multiply it by 1,000. Well, it's technically multiplying by 1,000. I just put an E3 after it, and I can just type that in my calculator and done. If in my problem I'm given centimeters, and I want to actually use that in my equation, I just put an E minus 2 after it. Done, it's converted. I don't care what number it is. If it was 0.5 centimeters, great, 0.5 E minus 2, done, it's converted. If I want to do millimeters, I just stick an E minus 3 after it, and boom, it's converted. If I want to do micrometers, so this is one of the new ones, we're going to see it more, so I'm not going to spend too much time on it now. That is E to the minus 6. Boom, just put an E minus 6. If I want to go to nanometers and I want to go to base units, I put E minus 9. It's great. This is how I do all my unit conversions. I'm not multiplying by 1,000, dividing by 1,000. I'm not doing any arithmetic here. I just chuck this after it, and boom, I've done that. If I'm multiplying by 10 to the minus 9, it's the same thing as dividing by, whatever this number is. 1, 2, 3, 4, 5, 6, 7, 8, 9, a billion. Great. I've divided by a billion. Did it. Yay. Easy. So, great. You're going to see me do that a bunch whenever I do unit conversions. I'm not going to actually plug it in and divide by 1,000. I'm just going to chuck this thing after it and call it a day. Real quick, real easy, real simple. All right. I know this says 2054. Don't worry about it. It's the same stuff. Boom. All right. Charges, yay. Pictures, cool. Okay, so here's the things we're going to talk about. We're going to talk about charge. We're going to talk about charges transferred. And then we're going to talk about forces. That is basically this entire PowerPoint. So, a little bit of background. You all have seen this, hopefully, fingers crossed. No one was born knowing how the universe worked. That's just not how it works. No one was born with basically any knowledge of the universe. Everything has been discovered, everything has been built on prior discovery. That's how human progress works. So, the classic example here is the atom. No one was born knowing an atom even existed. So that went way back to the Greeks, and someone decided they would keep cutting something and eventually get to the smallest thing and call it atom. I think it means the original word was something like unable to be cut. Whatever. Fast forward a bunch of years, we introduced something called charges. We're actually going to do a lab to discover that there's 2 types of charges, again, because that's something that you've probably heard before. You probably know there's 2 types of charges. How did they figure that out? It was not written on a stone in a cave somewhere. Someone had to figure that out. You're going to do an experiment that Benjamin Franklin did for that. So you got the plum pudding model of the atom, everything's all mixed in there, yay. Then you have Rutherford's model, where you have a bunch of electrons orbiting around it. Again, none of these were quite correct. They keep getting improved, and then the one after that is the quantum model. I don't have a picture of it here, but the electron cloud actually does show up in the later slide, where we don't actually know where the electrons are. It's a fuzzy thing, probability, it's really complicated, it's a great time. So, all that to say, things keep progressing. Charge exists. There's been work done to show where charges come from. You all can kind of remember that from your chemistry classes. They spend more time on that. Charges. What are they? They are something we discovered where basically there was a force that we saw that wasn't explained by gravity. And so we said, why does this exist? We said, things must have charge. So for now we're going to introduce this and we're going to be able to get into a bit more. So the property of matter, which results in the matter experiencing a force through electromagnetic fields. That's going to sound really funky, but it's going to make more sense as we go through this PowerPoint. So for now, don't worry too much about the definition. I'm never going to ask you on the test, hey, what's the definition of charge? That's not going to show up. But there it is. You do need to know the unit. The unit is Coulomb, named after a guy whose name was Coulomb. This is going to be a trend in this class that basically every unit I teach you moving forward, because they were all discovered in the last 200, 300 years, they're all named after people. That's a really common trend in physics. Force, what's the unit for force? Newton, named after Isaac Newton. That's one from Physics 1. The other one's from Physics 1, I honestly don't know where unit comes from or kilogram. But every unit in this class is going to basically come from someone's name. So Coulomb is the one for charge. You're like, why is it Coulomb? Because he discovered it. C for Coulomb. The variable is Q. Why is it Q? I actually don't know. I have no idea the history behind it. I don't know. You might want to say, oh, it's charged, so we use C. But C is used for capacitance. So, we run out of letters. Remember the differences between units and variables. It's very easy to mix these up. Units are the thing you put after the number. It's going to sound maybe trivial to some of you, but you will make this mistake at some point. 5 coulombs, that's how much charge I have. Great. What is a variable then? A variable, and this is an equation that we're going to see later on. Don't worry about it right now. Don't worry about this equation. You're like, where's this coming from? Don't worry about it. All I'm showing you this for is that this equation, Q represents charge. So Q is a placeholder. It is a shorthand for charge. Unit goes after the number to tell you that it is a measurement of charge. Q is what goes in the equations. 2 different things. Variables and units. You know, the example for you all is the unit for distance. So if we think of distance, just to connect this to something that you all are cool with, the unit for distance is meters. The variable would be, you know, X, Y, Z, R, D, there's a bunch of them. So that's just to kind of think that. All right. All charge is multiple of 1.6 times 10 to the minus 19. I'm just telling you that now, but it'll make sense when we, where is that coming from? We'll spend a few more slides on that. For now, though, this is a nice little summary of kind of all the major points with charge. Last little thing, lowercase q is for a single charge, a point charge, meaning a charge that exists at a point, a thing that takes up no volume. Capital Q is if you have a bunch of them. So, like say I charged up my water bottle, it would have some charge capital Q. If I picked some infinitely small point and I said how much charge is there, I'd put a little q there. Kind of like mass. You could have a point mass, which is the mass located in an infinitely small kind of dot. Capital M mass would be all the mass of the entire object. All right, think about this. Give you all 30 seconds, minute, chat with people around you, see if you can come up with an answer. What is the smallest amount of charge you can have in water? Think about it, chat about it, see if you can get the answer. I'm going to ask you all. Oh, and I'll clarify non-zero. Non-zero. Non-zero, 0 is the trivial one, that's boring. Non-zero amount. Assuming you have charge, what's the smallest amount you can have? Alright, what are some guesses? What are some guesses? Yeah. Alright, why? You can have one charge, that's good. What? And then this will be a nice tangent to someone else. So you can have one charge. What are the things that have charge? This is a chemistry question. Protons and electrons, great. So, great. This is a chemistry basically review. What is the smallest amount of charge you can have? 1.6 times 10 to the minus 19. Why? What has charge? What fundamental objects have charge? Protons and electrons. And this is again going to be one of those asterisks. That is the smallest unit of charge that you can have with an asterisk. Something you may not have learned in your chemistry classes. Again, you're always learning. Turns out, you can break electrons and protons into smaller objects. They're called quarks, and they have like 2/3 of a charge. And there's ones that have positive in mind. Yeah. So, and then what are quarks? Quarks are made of more things, and those are probably made of more things. And then, how far does it go? Who knows? For our purposes, we're going to pretend like quarks don't exist. Don't worry about it. So yeah, you got your protons, you got your electrons. This slide is kind of not the best organized. What else are we going to go about? For our purposes, and for all you need to know, this is good enough for pretty much everything, unless you're doing particle science, unless you're doing high energy physics. A proton has positive 1.6 times 10 to the minus 19, and an electron has negative 1.6 times 10 to the minus 19. It is exactly equal but opposite. Now, their mass is different. The mass of a proton is 1,000 times larger than the mass of an electron. They're both still tiny, so tiny that like this number is easy to write down as scientific notation, but it would actually be hard for me to fit on this paper because I'd have to have 31 zeros. 30 zeros followed by a number. It is such a small number you cannot conceive of how small it is. So an electron is 9.11 times 10 to the minus 31 kilograms. Proton is 1.67 times 10 to the minus 27 kilograms. These will be given on the formula sheet. They do show up in problems here and there. But yeah, that charge is the important one. You can have zero charge. All that means is you have equal protons and electrons. Technically, everything probably has slightly imbalance, but we approximated that. So like my water level right now is roughly uncharged, roughly. It's probably slightly charged one way or the other, because it's almost impossible to have exactly equal amounts. Most objects approximately have a charge of zero. It does not mean that they have zero protons and zero electrons in them. That is nonsense. If you tell me an object has zero protons in it, then what is it made of? That's kind of the question, and the answer is protons and electrons. So, when something is neutral, when something is uncharged, it just means it has equal amounts. Therefore, when something is charged, it means it has more of one than the other. If it's negatively charged, more electrons. If it's positively charged, more protons. That's what that means. Now, quick little tidbit is going to come into play later on. It is very hard to take protons away. Very, 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 very hard. They're stuck in the nucleus. For you to take a proton away, it means you literally have to split the atom. When we transfer charge, we are not doing nuclear reactions. We are not doing fission. We are not splitting atoms. So whenever we transfer charge, we are not moving protons. Because you would fundamentally have to be ripping them away, or you would have to be pulling, this does sometimes happen, hydrogen atoms. You can move hydrogen atoms, which are effectively one proton and an electron. Electrons are the ones that are moving, hence the name electricity. Whoa, electricity, electrons, there's a reason. I don't know if it's the reason, but it's convenient. So, electrons, whenever we charge something, we are actually either adding electrons or taking away electrons. If we take away electrons, we made it positively charged. If we add electrons, we make it negatively charged. Okay, I still haven't told you where, I am skipping. I told you where to go through some observations. How do we even know protons and electrons exist? How do we even know there's two types? You are actually going to do a lab on that this coming week, the same one. Benjamin Franklin was actually the one that discovered there was two types of charges, which is kind of interesting and cool. Two with one positive, one negative. And so you all will do an experiment to see that yourself. No labs this current week. You all have labs next week. The labs are not tied to this course anyway, so if you have any questions about labs, contact your TAs. But yeah, your first lab will start next week, and you'll be doing that experiment that he did to discover the two types of charges. So, okay, charge is quantized. Quantized is a fancy word meaning you can count it. It is a multiple of E. E is 1.6 times 10 to the minus 19. This E is just the fundamental charge, it's almost like E for electron. This E just is 1.6 times 10 to the minus 19. Quantized is a word which means it's a multiple of. This is where the word quantum mechanics comes from. Quantum mechanics comes from this idea that energy levels are quantized, meaning around an atom, you can only get certain energy levels like a staircase, and you can look into that yourself. But in this case, if I say something is charged and I give you the amount of charge, that number will be nicely divisible by 1.6 times 10 to the minus 19. I might not give you enough decimal places actually for that to work, but that's fundamentally that is going to be a true statement in the world. Everything either has an integer number of extra electrons or extra protons. Charge is a conserved quantity. This is another fancy physics term, which basically means you can't destroy it. You can't destroy electrons, you can't destroy protons. Again, I'm putting a little asterisk next to that. You can technically destroy them, but we're not going to. The way you'd have to destroy them is colliding them really strongly, or you introduce the antimatter. Again, you're going to hear me mention these little caveats because they exist. But for our purposes, you cannot destroy protons or electrons. That's good enough for most of y'all. Same thing with physics 1, y'all learn mass cannot be destroyed. Technically it can. Don't worry, it can be changed to energy, but for our purposes, it cannot be. They charge by gaining or losing electrons. It's a bunch of things I already said. This equation looks Funky, but it's really trivial. You're going to see when I'll just do it real quick. If I had 10 protons, so let's just say NP equals 10. That's the number of protons. Number of protons, I'll even write it this way just to make it more clear. And say my number of electrons is 5. You know what, let's do the opposite just because it makes it a bit more interesting. Great, you just plug it in and it tells you your net charge. It's really trivial. This equation just says, what do I have extra of? Oh, I have 5 extra electrons, and it spins out a negative sign because electrons are negative. So we would get Q equals 5 minus 10 times 1.6 times 10 to the minus 19. So we get negative 5 times 1.6 times 10 to the minus 19, and that equals something. What's my net charge? Oh, what do I have extra of? If I have extra electrons, multiply that by negative 1.6 to the 19, 5 extra protons. So this equation, it looks more complicated than it is. It's a really basic equation that just says, hey, whatever you have extra of, multiply it by the fundamental charge. If you have extra electrons, it'll be negative. If you have extra protons, it'll be positive. Pretty trivial. Pretty simple, I should say. And I'll put the answer here, even though it's not very exciting. So in this case, we have 8 e to the minus 19 negative coulombs. It's negative because you have extra electrons. Woo. Really straightforward, really simple. Okay, great. Try it out. And you don't even, you could make up this equation yourself, really. It's not a profound equation. If you have 7 protons, 3 electrons, what's the net charge? I got answer A is 6.408 times 10 to the minus 19 C. B is 6.408 e to the minus 19 Q. C is 1.17 e to the minus 26 C. D is 1.17 e to the minus 26 Q. E is 7.32 e to the minus 19 C. F is 7.32 e to the minus 19 Q. And I guess to make the decimal places all equivalent, I'll knock off this. All right, here we go, about 20 more seconds. All right, in 5, 4, 3, 2, 1. Cool. So the question is, what's the net charge? So what are we solving for? We are solving for Q. Capital Q is the variable that represents net charge, not the unit, but the variable. All right, how do I get Q? I got 7 protons, 3 electrons, so how do I get Q? I do the number of protons minus the number of electrons times that fundamental charge. In this case, I have 7 minus 3 times 1.6 times 10 to the minus 19. And so 7 minus 3 is 4. So you get 6. It's a positive because you have extra protons. And the unit is C, not Q. So again, do not mix up C and Q. It's easy to do so. 1 is the unit, 1 is the variable. In our case, we want the unit. The reason that this previously had an extra number is technically the fundamental charge is like 1.6019. It keeps going and going and going. 1.6 is good enough for us. But I previously had that from that. So yay, great, awesome. That's how it goes. All right, so easy peasy. Net charge, super simple. Okay, opposites attract, like charges repel. This is an observation of reality. Why do charges do this? Because that's how the world works. This is just one of those laws. How do we know this is true? You're going to do a lab on it this coming week. So, you'll get to see it, you'll get to discover it in the lab the same way they discovered it 100 years ago. Yes. Q is the variable, C is the unit. Yes, that's a good question, good reminder. It will happen to you. You will mix these things up. C is a variable for a different unit. It's capacitance. As far as I'm aware, Q is not a unit for any variable that I am familiar with. And I'm familiar with a lot of variables. So interestingly, whatever reason, we don't use Q for anything that I know of. But I'm sure someone does out there somewhere. There's a lot of things. All right. Opposites attract, like charges repel. Great. Observation reality. It's a law. It's a rule. This is not derived. This is not theoretical. This is experimentally observed. You're going to do this next week yourself. It's just one of those, it is what it is. There's not much in it, that's just a statement. What does opposites attract, like charges repel mean? This means if I bring two protons near each other, they will repel. If I bring two electrons near each other, they will repel. If I bring a proton and an electron near each other, they will attract. Observation of reality is what it is. If you don't like it, I didn't make the rules. I just tell you that. All right. We got to talk about insulators and conductors real quick. The section of it, I'm going to kind of zoom through. I'm not going to really test you on it, but it is an important thing that you all need to know. It's going to show up a bunch in this class. Insulators, the electrons are trapped. They cannot escape the atoms. They are trapped in that electron cloud. It is very, 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 very hard to pull them away. It is possible. Every insulator can turn into a conductor if you apply strong enough voltage. The example of that is lots of examples of that. Lightning is one of those. Air is an insulator. You get a strong enough voltage, you get lightning. Everything can become a conductor eventually, but you got to really work on it for insulators. Metals, conductors. So metals is an example of conductors, but the diamonds are conductors as well. Their electrons are free to swim around. This is something you've probably learned about in chemistry, hopefully. Their valence electrons, the ones farthest from the atom, are free to kind of swim around in the sea. They're free to travel, whereas in insulators, they are stuck. They're locally stuck. Okay? This is going to come into play. And the next one. Oh, and then an interesting thing. In conductors, the charge is spread over the surface, and we'll learn why. We'll need a couple weeks to explain why they go on the surface of things. But you'll always find the extras on the surface after you let it go. Okay, so here's the question, something I'm just trying to think about. I have a charged rod. It's not 100% clear here, so I'll explain it. This charged rod is extra electrons. And on the right, I have a conductor where the electrons are free to kind of travel around. They're not stuck. And in an insulator, they're stuck. And the question is, what will happen when I bring this extra negative charge near these objects? What will the charges in this object do? So, think about it. Give you all 30 seconds, a minute to just think about it yourself. And then I'm going to show you what they do. Obviously, I can't show you physically. You can't see these electrons, but there's a simulation of this. This is a screenshot from the simulation that is accurate, well enough at least. All right, so the key here, opposites attract, like charges repel. If I bring this nearby, we can basically cancel out the electrons and protons here and just pretend this has a bunch of electrons on it. So if I bring a bunch of electrons near these objects, they're going to repel all the electrons in that object and they're going to attract the protons. Now those protons cannot move. You're not going to be moving those atoms. It's too difficult. So really the electrons are going to be the only ones that behave. You all can try this out kind of whenever. It's posted. The link is here. But for the sake of time, I'm just going to kind of show you all. So this is the website where I got this from. I think it's one of the best kind of simulations I've seen of this. So this is the same exact thing where it is charged. And as I bring this closer and closer, there is a distance dependence. So you notice that the conductor, we'll kind of look at that one first because it's the easiest one to look at. The electrons got pushed away. They got pushed away, so I end up with extra protons on the left, and I end up with extra electrons on the right. because they're free to move, so they do. They escape, they get as far away as they can. Now, some will still kind of zip their way over here, that's fine. The insulator was much more subtle. And so we're going to look at the insulator as I'm doing this. Something still happens in the insulator. They still move, they're still confined to the atom, but they get stretched to the right. That electron cloud gets stretched to the right. So what ends up happening is it's as if there's extra electrons on the right still, and it's as if there's extra protons on the left still. Not because they were able to move all the way over here, but on average they shifted to the right somewhat. Previously, we kind of thought of it like center mass. They were previously all kind of at the same place. Now their kind of centers are shifted. So it's as if there's more electrons on the right. What is the net result of this? And this is like the fun experiment you all seen this. I should bring it something. Basically, if you charge something and you bring it near an uncharged object, regardless of what that object is, they will be attracted to each other. So if you charge a balloon, you know, I've seen this in, if you've been in any physics class, this is like a classic, and I'll try to bring a balloon on Friday. If you rub a balloon on your hair, you charge it. If I bring it near the wall, it will stick to the wall. Why does it stick to the wall? Because it's pushing the electrons away in the wall, and by pushing them away, the protons are closer and they're attracted to each other. We're going to learn that distance matters. I haven't given you that equation yet. The closer things are, the stronger the force. So even though the wall is an insulator, we call this a dipole. It gets polarized is another phrase for it, but it makes this dipole. Dipole means two poles. You get a negative and a positive. Positive is closer, so it sticks to it. This balloon and water trick works on everything. You can charge that balloon, you bring it near some paper, the paper will get attracted to it. You bring it near a stream of water, the stream of water will get attracted to it. You bring it to a metal, it will work. The problem with the metal is if you touch it to the metal, these charges will then move to the metal and it'll discharge really quickly. So that's the bummer with the metal. You might not be able to see it as much. Also metals tend to be a bit heavier, but if you had some light piece of metal, they'd kind of jump to it. So here's a nice little picture of this. Things get, in this case, you bring a positive. Things get polarized when you bring charge near them. I'm not going to really test you all too much on this, but this is just something that's important to know. This is how charges behave when you bring them near each other. There's not any math problems with this or anything like that, so that's why I'm not going to focus on it too much. But it is important for you all to know that charges will get pushed and pulled, and the closer they are, the better. All right, so let's see if any of that landed. So here's a question. I have positive and negative charges. So I'm going to need to explain this kind of thing because there's a lot going on here. Answer A basically says that I bring a positive charge near an insulator, and the insulator is attracted to it. Answer A also says that if I bring a negative charge, it's repelled. So basically the question is, as I bring positive charge near an insulator, will it be attracted or repelled? As I bring negative charge near an insulator, will it be attracted or repelled? And this insulator is uncharged. So basically, if I bring extra charge near an insulator, what will it do? And does it depend on the type of charge? Will it be attracted or repelled? And does that change depending on whether or not you bring a positive or negative charge? That's the question, to see if any of this landed.
If you bring an electron, what will those
So each of these is independent.
I feel like even though it's stress.
All right, we'll go like 20 more seconds. All right, in 5, 4, 3, 2, 1. And so this idea is going to be important for your lab this coming week. Again, it's helping us understand that. So let's kind of just draw a situation up here. So as I bring this positive charge close to an insulator, what's going to happen? Well, the electron, I'm just going to draw one electron cloud because it's going to be a pain in the butt to draw a bunch of others. So let's just pretend that, all of them are going to do this. So here's let's pretend this is made of one atom, but it's made of one atom. As I bring it closer, opposites attract, like charges repel. As I bring it closer, that atom itself cannot move, but its electron cloud will stretch, will get pulled closer to that. Why is that significant? Now that the electron and the protons are closer, they're going to experience a stronger attractive force. There is still a repelling force on this proton, but it's smaller because it's farther distance away. How do we know that distance matters? It's the next slide. We'll see that in a second. As you get things closer or farther, that force is stronger or weaker. Closer is stronger, farther is weaker. So if I bring a proton near this, it will attract because it'll pull those electrons closer. Because they're closer now, it will attract. When I bring an electron near this object, so we're going to start with the same thing. We're going to have our little proton, and then we're going to have our electron kind of, swinging around it, this electron cloud. As I bring it closer, it's going to stretch it the other way. Opposites attract, like charges repel. So this positive charge is closer, so it's going to get a stronger force. This is going to get repelled, it's going to get weaker. So the net force, in this case, will be to the left. It's arrows. Bigger arrow, smaller arrow, they cancel out. Bigger one wins. So in both cases, it attracts. In both cases, it attracts. If you bring a charged object near another uncharged object, it will always attract. When I charge a balloon on my hair, I actually have no idea whether that balloon is positive or negative. There is no easy way to tell that unless you had another negatively charged object. If I charge that balloon, though, and I charge another balloon, they will both be charged the same. Why? Because the reason that the mechanism that they charge, they're identical. So they're going to both get the same thing. Whether that's both, you're going to get extra positives, or both extra negatives. So if I bring those near each other, they will repel. If you have two similarly charged objects, they'll repel. If you have two oppositely charged objects, they will attract. It's almost like this is not the same mechanism that I'm about to tell you. The mechanism I'm about to tell you is not the same, but the logic is the same. When you all play with magnets, it doesn't matter whether you bring the north end or the south end near a metal, it still attracts. That is a completely different thing going on there, but just that same idea is true. You can't actually determine which end of a magnet is unless you have another magnet that you know which end is north and south. Alright, so, great, there's that. Again, this is one of those things that's surprising people, but it attracts no matter what. Okay. Last thing I'm going to kind of tell you, and this will be what we then spend all the next class on, this is the actual equation. Coulomb's law, 1700s, hot minute ago. Coulomb, the guy that Charlie's named after, there he is. Wow, awesome. He discovered that the closer you move charges, the stronger the force is. This is his contribution. He discovered that when you bring charges near each other, the force gets stronger the closer it is. And that's a pretty easy thing to do. You get two objects that are identical, you charge them the same, you bring them near each other, and you see that they push stronger when they get closer. Again, you're going to see it this coming week. It's really simple. This is the equation that we're going to spend next class working on. The force between two objects, F stands for force, equals K. It's called Coulomb's constant. It's a really nice number. 9 times 10 to the 9. It'll be on your formula sheet. It's a constant. 99. Super easy number to remember. You're going to end up memorizing it because you're going to have to use it a lot. 9 times 10 to the 9. Q1 is charge 1, Q2 is charge 2, and R is the distance between them. The reason we use R is these can be anywhere. They're not just like left, right, up, down. R is that radius. It's a distance between two things regardless of where they are in 3D space. This is a vector, so we're going to have to deal with that. Don't forget the squares. We're going to practice this a bunch next time. The whole next Friday is just going to be using this one equation. It's going to be great. It's a simple equation, but we're going to need to learn how to use it. Have a good one, y'all. I'll see you all Friday.